Good morning. For the people who just came here, I'm Larry Gould, and I'm chairing this session. And this is a very, very exciting year for physics and for science in general. In 1915, Einstein's created his general theory of relativity, and also in 1916, it went from 15 into 16, the issues of gravitational waves, okay? And in the United States, we have a celebration on the 4th of July, you know, fireworks. So it's like nature said, what can I do to celebrate Einstein's 100th anniversary of general relativity? And nature then answered, well, let me produce some gravitational waves. And the first speaker, Professor Benno Willke, you can see he's at the Leibniz University at Hanover, and he's also associated with the Max Planck Institute for Gravitational Physics, Albert Einstein Institute, and he is the primary person in charge of the laser installations, which is the heart of the apparatus for the detection of the gravitational waves. So now I introduce Benno Willke, please.
Thank you very much, Larry, for the kind introduction, and thanks for the organizers to invite me to this conference and give me the chance to talk to you about this spectacular event that we saw last year. And you might say, well, spectacular, this word is used way too often these days. So please judge yourself. What happened? About 1.3 billion years ago, two massive objects circled around each other and merged. They produced a wave in space-time which traveled for 1.3 billion years with the speed of light towards the Earth. On Earth, these waves changed 4-kilometer distances by less than a 10,000th of a proton diameter. And laser interferometers were able to detect that, and scientists were able to look at these signals and figure out that they were produced by black holes. So that's the story in short. It's up to you to decide whether you find it interesting. If so, stay with me and I'll explain more about it. So at least the Physical Society found this very interesting. We made the cover page of a very important journal in physics, Physical Review Letters. This was not done by one person. The author list has 1,000 authors on it from 133 institutions. And not only we find it very interesting, but if you judge the importance of the publication by looking at its online relevance at metric, this turned out already now to be the 10th most important science output they ever registered out of more than 5 million science outputs. Prize committees as well thought this was very good and very important, so these 3 persons already received a couple of prizes, and I think they are now very happy that they started many years ago in gravitational waves. But let's come to the physics, to the reality. What I would like to discuss with you is how can we listen to the universe? Why do I write listen? Because this is really the dawn of a new type of astronomy. We don't look anymore to the universe with one sense, like the human eye, but we use a different type of sense, like the hearing, to now look at different things in the universe. So since mankind exists, we look at the heavens and see stars, and we of course use instruments since Galileo to look further out in the sky, get more information about the universe. And these days we use large telescope like this radio telescope here, and don't really use the eye anymore, but a more sensitive device, the CCD camera, to look at things in the sky and get information about it. Now the question is, how can we hear? Obviously not in this way. I mean, you can go to the quietest place on Earth, put your ear against the sky, and you won't hear anything. So we need to discuss how we can use something like in these radio telescopes to make our sense, our hearing, better, and that is called a space-time detector. And if we do something similar here, then we hope that we get an output, not as a nice picture here, but as a sound, which could sound like this. So okay, that's what we try to hear. Okay, now let's try to understand how hearing the universe could be done. But before we do that, I would like to take you on a small journey about dimensions. If we look at the person who is typically around 2 meters tall, and take his size or her size and multiply it by 100, we end up with something which is a football or soccer stadium. If we do this again, we already have the size of a city. So please imagine that we put a person into the soccer stadium, 100 people behind each other, and that is what such a step here means. Okay? We do these kind of steps, and we continue with them. Now we have already Germany as a factor of 100, the diameter of the Saturn rings, in a solar system, whole solar system, Oort cloud, almost Andromeda, 1,000 stars, Milky Way, and we go on, and each time we multiply by a factor of 100. Okay? So this we indicate by these exponents. 2 here means factor of 100. So this means 11 times the factor of 100. And the sources that we look at are even further out than this. But we need to do a journey in the opposite direction as well, to the small dimensions. Okay, let's do that. So here we have a fingernail, thumbnail, we have a mite here, bacteria, DNA, standard cell, X-rays, atoms, quarks, and we need to go further in this direction. So this talk will deal with objects out here, and they produce something which is out here. So this really covers a lot of dimensions in space. Okay, can we hear tones from the universe? You might say no, because there's vacuum. And I'm with you. Sound cannot propagate in vacuum, so we can't hear regular sound, which is a change in density and pressure, because there is no medium. But Einstein can help by designing a space-time sensor, and the key physical quantity that we have to look at is gravitation. So Einstein, let's look at gravitation. Gravitation is what keeps me on the ground, so we fall onto the ground, but we do not really fall. I mean, sometimes apples fall upwards, so what Newton said is that all mass exert an attractive force upon each other. And that's the reason why the apple tries to attract the Earth, and the Earth attracts the apple. We normally don't recognize that the apple attracts the Earth because it moves only very little. Albert Einstein now said, well, I have a different notion. I say gravitation is not a force, but a property of space. What does that mean? Well, he wrote that down in his general relativity theory, which could as well be called the Einstein's theory of gravitation. He says that matters determines how space bends, and space determines how matter moves. Okay? Let's try to get an intuitive picture on that. Here I have something which looks like, you can imagine as if it was a rubber membrane, and if we put the Earth into this rubber membrane, it would bend the rubber membrane, and the moon would now know how to move around the Earth, not because there's an attractive force, but because the space-time is bent. And this is an appropriate way to look at things. We now know because not only matter knows how to move, but light as well knows how to move, and that cannot be described by Newton's theory. So we see something which is called gravitational lensing. Let's first look at what does a lens do. It takes a light beam and bends the light beam such that it combines with all the other light beams here and produces a sharp image. And the same thing happens with gravitation or space-time curvature. Assume that you have a telescope here and look at this distant galaxy. If there's another galaxy in between which bends space-time, then this causes the light rays not to move straight anymore, but to bend and show up at this telescope. And that produces these Einstein arcs. And here's another picture which describes what gravitational lensing can do. We look with a telescope on Earth to a supernova which is 9 billion light years away. And we wouldn't see it because it's normally too faint. But because there is a galaxy cluster in between, about 4 to 5 billion light years away, the light rays get bent, and we see the picture of this galaxy here in this picture, not only here, but as well there's a picture here, another one here. And this inner part is very interesting. Here's a zoom-in version, because there's an elliptical galaxy here, and that produces these 4 images of this one source. And these are now 50 times brighter than they would be without this lensing. So that's very helpful in astronomy. And this is the so-called Einstein cross, the famous name for this effect. Okay, so if this space-time bending seems to be appropriate, then let's look what happens to our space-time if we put a heavier mass in there, because the bending obviously is connected to the density of the stuff that we put in. Okay, so if we put larger things in, the space-time bending might be very extreme, and this causes now light, once it enters, that it can't leave anymore. The bending of the light rays is now such strong that the light cannot leave. Okay, and this is what we call black holes. Do we have any indication that these black holes exist? Well, we have indication that these very heavy mass densities exist from looking at the center of our galaxy and how the stars move around the center of our galaxy. You can see how all these stars move, and they seem to move around an object here in the center, which causes all these objects to move, this gas cloud as well, which we expect to move as well around. And by looking at the motion of these stars in our center of our galaxy, we can now determine that there should be 4 million heavy solar mass type heavy black hole here in the center. But it's black, so we won't see it at all, because no light, no electromagnetic wave will ever come out of this black hole, so we can't see it. Now, let's look at our 2 black holes that I will talk more about later, and assume that we could look very close to them. We could see the gravitational lensing of these black holes. So imagine we had this picture of the sky, and now we put 2 black holes in front. Then it looks like this. So this is what the gravitational lensing would do to the stars, to the light of the stars. And if they now even rotate around each other, this would be what we could see with naked eye or telescope if we were close enough to resolve these black holes. Unfortunately, or fortunately, you can determine what you want, we will never be able to come that close. We wouldn't stay there long, but we will never have a chance, at least I cannot imagine to have a chance to see this gravitational lensing really with this resolution. So we need something else. Well, if there is this space-time bending, and we have a dynamic thing, 2 objects rotating around each other, then Einstein says, well, then we get something which is similar to electromagnetic waves or water waves, but now not on the water surface or in the electric and magnetic field, but in space-time. Now, space-time bends, and these ripples propagate out with the speed of light, and they change the space-time. So that is what is called the gravitational wave. Accelerated masses create space-time deformation that propagate at the speed of light. And these accelerations have to be asymmetric. Symmetry wouldn't work. We need some asymmetric acceleration of masses to produce this gravitational wave. Okay, now we know what gravitational waves are. And let's ask ourselves, do we have any indication that these exist? And there we can say yes. Hulse and Taylor many years ago looked at two neutron stars, one of which is a pulsar. They put a telescope here. They looked how the orbital period now changes, and that can be predicted by the loss of energy due to gravitational waves. If gravitational waves exist, these guys have to produce them, lose energy, and if we look at the orbital period and plot that, here's the orbital period, over time, many years, 25 years, then we get these dots, and prediction by energy loss due to gravitational waves is like this. So this is not that they detected gravitational waves, they just said if they exist, how would the energy loss then be? And even for that, they received the Nobel Prize in '93. Okay, but now let's come back to our two binary black holes. You might see them here. Now, if gravitational waves exist, they rotate each other and produce these gravitational waves, which are now indicated as green color here in space. And they now propagate, okay, through space with the speed of light. Speed of light means that a beam of a laser, if it could just travel to the US, would take a fraction of a second. And with that speed, these guys travel. Now, we don't have the time, but I would like to tell you when this happened. This actually happened if you look at the history of Earth. This happened at this point in time when the first supercontinent Rodinia was formed and when the first mononuclear cellular algae were formed. So at that point in time, this event happened. Okay, we don't have the time to wait for so long, so I accelerated my video, and now 1.3 billion years later, it hits Earth, and this is the effect that it produces on Earth. Largely exaggerated, so don't be afraid that this really happens, but this is the effect. Yeah? So Earth gets deformed like this, and now it's over. So if we were able to have detectors for this small period of time, that would be nice. And now you might imagine how gracious nature was to us. It knew already 1.3 billion years ago that we would celebrate Einstein's 100th anniversary this year and produce these gravitational waves. Okay, now, effect on Earth. The effect on Earth is like this. If we had three masses, let's assume we have one here, one here, one here, and we fix a coordinate system here around this mass, then the effect of a gravitational wave would be that this mass moves away and towards the center mass, and with the opposite sign, this guy wouldn't move. So this would stretch when this arms get short. Okay, that's the effect, and that's the effect that experimentalists now have to measure. Looks simple from the first sight. But now let's look at how much this change really is. If we have a 4-kilometer long distance between these masses, then the distance would not change by a diameter of a hair. It would not change by the diameter of an atom. It would not even change by the diameter of a proton. It would change by 10 to minus 19 meters. Okay. Now you probably agree with me that this measurement task is not that simple anymore. So how can we do that? Fortunately, there exist things which are laser difframeters, and if the mirrors move, they produce a changing light intensity here at the output. How do they work? They have a laser here. The laser beam is split, and half of the beam travels in this direction, the other half in that direction, come back, and then half of the stuff that comes back from here is now reflected in this direction, and half of the light that comes from here is transmitted and goes in this direction. And now you might ask yourself, well, light comes from here and light comes from here, so I have light plus light. Can that give darkness? Yes, it can, if we understand that light is formed by waves, by electromagnetic waves. So if we now send out a wave, they have maximum and minima. They go to the far mirrors, come back, hit the beam splitter, and there they combine, which we call interference. And they can combine such that the maximum comes to minimum, then it's dark. But now if I move the end mirrors a little around, they can combine that maximum comes to maximum, and then it's bright. That's what is called interference, and that's what gave the name to these laser interferometric gravitational wave detectors. So we have a laser and an interferometer. Okay, now we have this thing here, laser, our beam splitter, and now you might recognize I've put my 3 dots here that I had before, and I get an output. And now my measurement task is to measure the brightness difference at this output. Okay, I just put a photo detector there or a CCD camera and measure this brightness change. Again, seems simple. However, if we look at by how much this brightness really changes, then we need to first look at how the output power of such an interferometer would depend on the arm length difference. Here it goes like a cosine square. So if I have a delta L change in the differential arm length, in the difference between the two arms, which is, by the way, the strength of the gravitational wave multiplied by the length of the arm, if I have something that changes its length by this over time, then I would move up and down on the blue curve, and I would get a power change at the output. And this formula already can be used to explain to you why do we make our laser interferometer that long, 4 kilometers? Because the thing that we need to measure scales linear with the length. For the given strength of the gravitational waves, if we make our arm longer, then our measurement tasks get easier. Get easier, that's good, because the measurement task is quite complicated. We need really to zoom in here. And if we do that, then we have here a length change of 10 to minus 18 meters, and that produces a change of our input power by 10 to minus 12, a fraction in 10 to minus 12. And there are many, many problems, including technical noise of the laser, shot noise, and so on, why we don't use this operation point, but a different operation point, but I have really no time to go into it. So this is the measurement task. We need to measure this output change by very, very tiny amounts. And again, now if we increase this power of the laser, the power that we send in, our measurement tasks get easier, because we see for a given gravitational wave a stronger change in output power. So we want long arms and a lot of power in these interferometers. Now, 10 to minus 18 meters seems unrealistic. Let's look what Michelson did with his first interferometer when he invented this. Here you see the same thing. He put it on a granite table. Morley and Michelson invented a new scheme where they just folded the beam a couple of times. And already in 1987, they were able to measure length difference of 600 picometers. This is 0, and then we have 9 zeros, and here there's a 6. And our job is now to put another couple of zeros here and measure it. So we need to improve this concept by quite a bit to be able to measure this gravitational wave. Okay, so here is how it works. Laser, interferometer, gravitational wave comes in, out comes power fluctuation. Unfortunately, there are many noise sources that would produce the same thing even without a gravitational wave being present. For example, power noise of the laser, frequency noise of the laser, index of refraction fluctuation in the beam path. So this is similar as if you would drive on a street in summer and if there was really a bright sunny day, then you would see the image of the far distant hill or so to fluctuate. That's the same effect. That is this index of refraction fluctuation in air. Thermal noise, seismic motion. So if you would just put your mirror on the ground, fix it on a table which is fixed to the ground, it would move already by 10 orders of magnitude too much. So you need to do something about this ground motion, and there are many more noise sources which would produce a signal like this. And remember, we want to find this. So you would agree that it's very hard to see this. So now how do we technically do that? We put everything in vacuum. If we have vacuum, then we don't have index of reflection fluctuations and don't have to worry about that anymore. Here is the large vacuum system at the central station where the beam splitter is. Here's a normal ladder. Here you can see people working the vacuum. We have to be very clean dust particles on our mirror would really disturb the measurement by too much, so we couldn't measure gravitational wave. This is how people put one of these end mirrors of the interferometer into the system. And now let me try to explain to you how we deal with the seismic motion. So if we just put the mirror on the ground or suspend it from a platform like this, and the platform moves, then the mirror will move as well. So I don't have a platform, and I forgot my tennis ball, so I decided that I would try to do it in a different way. Now look at my apple. Imagine that this apple is now a mirror, and this is the ground. Okay, this is just a suspension, a strong, heavy structure that is here. Now if the ground moves, then you see that the apple moves as well. And the apple moves by the same amount, the same distance as my suspension point moves. Okay? Now I do something else. I move my suspension point only very little. Look at my suspension point, how much it moves. Almost not visible. But the apple moves a lot. And that's what we call resonance. Now comes the tricky part. Now I try to move my suspension point by a lot, but fast. And look what the apple does. Okay, my suspension point moves a lot, but the apple stays still. And that is the effect that we try to use for isolation against seismic motion. We have something which is called a transfer function. This is the frequency with which the Earth moves. We are here, and this is a transfer function of the pendulum. Don't worry too much about this graph, but for experts, they understand what I mean. If I now move only a little, the mirror would move much. This is a resonant feature at the resonance frequency, and if I move now fast, this mirror would not move, almost not move. And now I'm here, and this curve tells you by how much this motion is suppressed. So here it's suppressed already by a factor of 20 or so. And therefore, we need to suspend all our mirrors. The beam splitter is suspended, the end mirrors are suspended, there are more mirrors in the beam path. I again have no time to discuss that. For experts, we put Fabry-Perot cavities in the interferometer arms to get a longer storage time or a larger buildup, larger power in the arms. Anyway, these mirrors need to be suspended as well as the beam splitter. And you can do this trick again and again and again. So if you do it now with a triple suspension, with a triple pendulum, you would not get the green curve as a reduction, the blue for double, and the red for triple. And in reality, some of our experiments, the advanced Virgo experiments, use 7-stage pendula, and for advanced LIGO, we use 3 stages of pendula. The last stage of the suspension, so this is the main mirror, which is, by the way, something like 20 centimeters in diameter. The last stage of the suspension is not done by steel wires, but by fused silica fibers. We fabricate very thin fused silica fibers and weld them to the mirror and to the penultimate stage. And that we have to do to increase the mechanical Q of these pendula to reduce the thermal noise. Okay, so this is for the monolithic suspensions. And here's now again the curve. Here's shown the strain. This is the sensitivity as a power spectral density over the frequency of the gravitational waves. Here's, for example, 10 to the 2. This is 100. This means that my gravitational wave comes in at 100 hertz. It would oscillate 100 times per second. And this, the height of this curve gives us an idea what the sensitivity is. The lower, the better. And here you can see many noise sources. I have no time to go into that, but we are eventually limited by this red curve, which is the thermal noise of the mirror coatings. And here we are limited by quantum noise, and we can help this quantum noise here, only this is the purple curve, by increasing the light power. And here comes part of my personal contribution to this. We need to have high power lasers. Here's a sketch of the high power laser that we use for the advanced LIGO detectors. We start with a 2-watt laser, have some preparation of the light beam, inject it into an amplifier to 35 watts. Here we have another amplifier to 200 watts. We need some filtering. Here are some quantities which are only for experts, less than 0.1% higher order mode content, very good spatial beam profile, low power noise, low frequency noise. We need high power and simultaneously high stability in power, color, and propagation direction. And these type of lasers don't exist. No one in industry needs high power lasers with these properties. So therefore we had to develop the lasers ourselves. We did that with the Laser Center in Hanover. We fabricated these lasers in Hanover, 4 of them, put them into sea containers, put them on a boat, shipped them to the US, and my team then went to the US and installed these lasers. Here's the installation of these laser systems in a clean room at the LIGO gravitational wave detector site. We finished this by 2011, and since then these lasers operate reliably. Now, the optical layout is even more complicated than just this interferometer. We have a laser, we have another mirror here, power recycling mirror, another mirror here, signal recycling mirror, the beam splitter, and 2 test masses in between. But again, I don't have the time to discuss why we do all that. Just remember that we need to measure this tiny fraction of power change at this photodetector here, and therefore we need all these tricks. And we actually need many more tricks. So it's even more complicated, and again, I don't have a lot of time to go into that. Scattering light, detector environmental monitoring, all the kind of stuff, all the tricks and techniques that come to our mind, we try to reduce the noise in these detectors. So we try to reduce all the spurious power changes at the output, not caused by gravitational wave, but by something else. But still, we can't really rule out that this power change was caused by something else and not by gravitational waves. So therefore we need multiple detectors far away. So as far away as possible, such that local disturbances can't disturb both detectors at the same time. And we need multiple detectors to figure out where these gravitational waves came from. And again, here hearing is a good description. We have no direction information with one detector. This would be the same if you close one ear. If you have only one ear, you can't determine where the sound comes from. You need the second one. And that's the same for these detectors. We need at least 2, better 3, to really decide where the sound comes from. Because if we wouldn't expect that the sound comes from from Earth, then we would as well need 3 ears to determine where in the 3-dimensional space the sound comes from. Okay, that we do. We have here a picture of the Earth. We have 2 detectors here in the US. We have 1 detector in Germany, where I work on. There's 1 in Italy. We plan to build 1 in India. There's 1 currently in construction in Tokyo. Here's how this looks, aerial pictures. These are the folks who are responsible for the proposal of the German detector. We have the LIGO detectors. 1 is in Hanford, Washington State. 1 is in Livingston, Louisiana. These are 4 kilometers long, and they always have different upgrade periods and detection periods. So we always try to detect them, we upgrade them, we try to detect them, so on. There's another detector here. It's this 3-kilometer long detector in Italy. This is currently under upgrade, so it wasn't operating when we saw these first gravitational waves. And here's a picture again, same type of curve. The lower, the better. This is the sensitivity that we had in the early detection runs till 2008, 2009. And this is now the sensitivity that we had last year in September. And you can see we went down by a factor of 3, but very important at these frequencies, at low frequencies, we went down, or we improved the sensitivity by much more than a factor of 3, almost a factor of 10. And this really allowed us to see these things. So on September 14 last year, the output, the power change at 1 detector output was like this, of the Livingston detector. And here's what happened at the Hanford detector. And this happened 7 milliseconds later. So if I just shift both by 7 milliseconds, then you can see that there's clearly something happening here. And we were never, we had never expected that we would see gravitational wave by eye. So this was really very astonishing to us. We all thought that it's an injection, that's man-made, that's not real. But it turned out it's real, and there, nature was really kind to us to produce such a strong gravitational wave with a signal-to-noise ratio of around 25. And here's how it sounds. It's very hard to hear because it's at low frequencies, and therefore it comes again at a little higher frequencies than reality. It goes, first you hear the noise, and then you hear the whoop. So this whoop, whoop, that's a gravitational wave. I'll play it again. Here you can't hear it because the sound system. Now we all heard the universe. This is really sound that came from the universe. Not as nice as the concert music last night, but it comes from something else. This was a very violent event. I'll say more about that later. So how do we now get information from that? We can now see it by eye, but we can't say what was the source of this. Okay, so therefore we need computers. We calibrate the data, and we produce ourselves a waveform catalog. So we calculate how a gravitational wave would look like if two masses would collide with different masses. So we have many, many waveforms, and then we compare these catalogs with the reality. Calculate something which is called the signal-to-noise ratio, and if both detectors have very good overlap with the identical waveform here, with the same time of arrival and the same parameters, then we call this a gravitational wave candidate. And now, this is not done by desktop computer, but to do this for really large computer clusters. One of the largest in the LIGO Scientific Collaboration is operated at the Albert Einstein Institute. So it has more than 3,000 computing nodes, many graphical processor units, a lot of disk space, and it's very fast. And with these type of computers, we figured out that this waveform here, that you can see here, is the best match that we can find for our data. Here's the waveform that we calculated from general relativity. Here is the reality, and here's the difference between the two, and you can see there's a difference, but no significant signal in there, only noise. The same here for the Livingston detector. Okay, and the nice thing is that we can now say a model based on Einstein's theory of general relativity is able to describe what we measure. Okay? It's not something that we didn't expect, but we can predict it by Einstein's theory of relativity. And here is what we use to calculate this waveform, which matched best. It were two in-spiral black holes. Here you can see the waveform. And this is very interesting here as well. Here's the time. Here you can see the velocity. And this is in units of the speed of light. Okay, so these objects were rotating at a speed which is more than half of the speed of light. Imagine you have two masses. Each has the weight of 30 suns, or a million Earths, more than a million Earths. And they rotate around each other. And not only at this speed, but 70 times per second with this speed. And that's kind of mind-boggling, at least to me. I can't really imagine that. They had very small separations. They came close to something like 200 kilometers, and then they merged. Here's what we can really extract from these waveforms. The black holes had 36 and 29 solar masses. The final black hole had 62 solar masses. More parameters here. Now, if you are quick and did the math, then you say, well, I mean, if I add up this mass and this mass, I don't get 62, but I get 65. What happened there? So the three solar masses were converted from mass into energy during this event. This event converted mass into energy, and a lot. The energy that was converted in this amount of time is 50 times the amount in energy that is produced by all stars in the visible universe. If we look at all stars, the light that is emitted by all stars in the visible universe, this event was 15 times brighter.
So there was eyes always instruments.
All instruments, in electromagnetic waves. And as I said, this converted the mass of a million Earth-type masses into energy in this 200 milliseconds.
This is the assumption.
This is what comes out of the calculation. If you add these masses, then you get that
Where
3.
do you get the masses? You can't, from where do you get the masses?
We get the masses from comparing the measurement with the waveforms that we have.
But you can apply any mass on this.
Can we just please hold the questions until Q&A? Thanks a lot.
All right, so here we have basically the size. It's hard to see, but since Europe here, we are somewhere here, I guess, and this is the size of these black holes. Could that be an instrumental artifact? Yes, it could, but we are pretty confident that it wasn't. We did everything we could to figure out, to clarify that there was nothing strange happening at the detector. No acoustic, no people around, no seismic motion. We did all that and figured out that all the other channels, we detect another 100,000 channels in our instrument, and all did not show anything that worried us that this signal was produced by something, but not a gravitational wave. How can we estimate, if we have this noise, how can we estimate how often such an event would happen by chance, just by chance? That we can do by taking the data of one instrument, and now we take the data of the second instrument and shift it in time. And we shift it by a longer time than the maximum time of a propagation of a wave would be between these detectors. Then the signal cannot be produced by a gravitational wave. And if we do that, then we do the same kind of analysis and figure out how often we get gravitational wave candidate, a similar gravitational wave candidate, just by chance. And if we do that, then we get this number statistics here. Here's the signal to noise ratio. This is what we get by chance. This is basically the strength or the loudness of the event. This is what we get by chance. And here's our gravitational wave. So it's far away from everything that we can get by chance. We calculated that such an event would happen by chance only each 600,000 years. And that means that the significance is larger than 5.1 for people familiar with statistics. Okay, there were many additional papers coming out, and you need to look for LSC publication in the web browser to figure out what else we found out. But we were lucky. At Christmas time last year, there was a second gravitational wave coming in. Here's the second gravitational wave, and it's hard, you can't see it in the data really. The black curve is what these computer recalculated what the signal was in here. And this is another gravitational wave coming from two binary black holes circling around each other. We now have 55 periods of the signal. Here you can see how the speed evolves when they come closer and closer. This time we calculated that it was a 14 solar mass black hole and a 7 solar mass black hole, and now you can see the merger. Okay. Here again are the numbers. Here's again the same plot of whether or not this could happen by chance. 14 solar masses, 8 solar masses. Again, some of the mass was converted because of some of these doesn't fit. Okay, now let's listen to them again. Okay, so these were the two, they were a little different, and this little difference was the one that we detected in September and the one that we detected in December. Again, you just listen to the universe. So here's the data run, September 2015, January 2016, what we observed first in September. We saw something else on October 12th. This is not strong enough for us to really claim it's a gravitational wave, but we are pretty confident it's of astrophysical nature. It doesn't meet the requirements for claiming a gravitational wave, and here's the third one, which is confirmed. And here's the plot of the knowledge that we had about black holes. So we knew that black holes of 10 to 20 solar masses exist from X-ray studies, but we did not know that these heavy black holes here exist, and we did not know that they would merge in the time of the universe. So this is the first clear detection of a merger of black holes of this size. This is a plot where we think they are on the sky. If you look at the sky, we have to point, but we only have 2 detectors, and therefore we can't really point very close to where they are. Now we have 600 square degree on the sky, so we need more detectors which are coming up to really identify where the source comes from. To talk about the future, let me just go a little back into the history. The whole field started with Joseph Weber, who first tried to measure gravitational waves with a cylinder, with an aluminum cylinder. He claimed that he had seen gravitational waves that was tried to be tested at different locations, one in Germany in the 90s here, this was in Munich. It became clear that the sensitivity of these detectors was not good enough to detect gravitational waves, so it was falsified. People started with laser interferometers. Here's the first one in Garching, another one in Glasgow, one at Caltech in the US, Glasgow in Scotland. And in the late 90s, we started to build these detectors. Here's a picture of the GEO600 detector that we started to build. It's a small, low-cost detector, but we developed many, many of the technologies which are now used in the LIGO interferometers to make them more sensitive in this small detector here. At the same time, the LIGO detectors were built in their initial phase, with the sensitivity not good enough really to detect gravitational waves. And the sensitivity is plotted here. So this is what we had in the first generation, up to the, say, 2009. And this is now what we get with the current upgrade, with the advanced LIGO. And we want to move further down. So we have the plan to go from the green to the blue curve. And there we have already design studies how we can do that. One design study proposes a gravitational wave detector underground to get rid of some seismic and man-made disturbances with 10-kilometer arm lengths built in a tunnel as a triangular, not anymore as a rectangular shape. Overall beam cube 30 kilometers, underground location, cryogenic squeezing, and 2 different interferometers. Here's an artist view how it might look like. Ground stations, cavern underground. And these caverns hold vacuum systems, multi-stage pendular. Here you see the size of people. So that's what we have as a design proposal. And this would meet this green, or this lower sensitivity curve. This would have a factor of 10 better sensitivity, which means that we would see a factor of 1,000 more sources. But there's one problem on Earth. We can do my apple trick or my pendular trick, but that only works at high frequencies. When I moved my apple slowly, I couldn't isolate the mass. It would move as the suspension point. So therefore we have something which we often call the seismic wall on Earth. We will never be able to see objects that produce gravitational waves with lower frequencies, like supermassive black holes if they collide. If we assume, for example, that we have a supermassive black hole as in the center of our Milky Way, that collide with another galaxy, they would produce gravitational waves as well, but at these frequencies here. We can't see them on Earth. And therefore we have the proposal to build a laser interferometer in space. Vacuum is for free in space, therefore you can really make it very long. So we plan to make it 1 million of kilometers long. That's a proposal. We have just successfully finished a test with the LISA Pathfinder with a satellite in space, which tested all the most sensitive technologies. So this is again a similar curve. Don't worry about details. These were the requirements that we wanted to test with our LISA Pathfinder experiments. These are the requirements that we really need for the full mission, and the red curve is what we get. So we clearly are much better than what we expected from this Pathfinder mission, and we are already extremely close to what we need for the final mission. So we are on good grounds for really building that detector. So, I hope that not too far from now, we have the LIGO detector, we have the GEO detector, we have the global detector in Italy, the detector in Japan, ground-based detectors, all data sent to these computers, data from LISA and from the Einstein telescope, and once we have that, then we will see signals with very clear signal-to-noise ratio on a daily, on an hourly basis, and then you would agree with me that then we really start to do gravitational wave astronomy. And with this look into the future, I would like to thank you for your attention and open for questions.
Okay,
There's probably some questions, so.
Concerning the second event, which was confirmed, I don't know if I've seen this correctly. It seemed to me that the amplitude is not monotonically increasing. Is that so? And if it's so, why? I have a second question.
So I think it's, I mean, it is increasing here.
No, the data. The data. This is the simulation.
Okay,
The data.
the data. So in the data you see that there is some oscillation here and that
Why is this?
spin. This is caused by, if I'm not mistaken, by spin of the black holes and then process it. And if the direction, so the direction of the angular momentum is now processing, is not that case?
No. Yes, the thought. So this is the white signal. I think that's what.
Yeah.
And so when the data analysis people saw this, they were extremely excited that maybe this is a hint of precision. But then what they realized is that quite probably this is due to just noise fluctuations, because since the signal is longer, some are more affected by fluctuations of the noise and the calibration. And so now there's no clear hint that there's actually precision in this.
Okay.
But it took them quite a long time to figure this out.
If I may, I have a second question. What is the sensitivity? What is the sensitivity of GEO? What is the sensitivity of GEO in comparison to LIGO now?
Sensitivity of GEO at higher frequencies is a factor of 3 worse, but at these low frequencies where we have these oscillations here, we are more than a factor of 10 worse, far more than a factor of 10 worse. So we would see if now a neutron star with the same signal-to-noise ratio would be detected by LIGO, we would see it, but not these black holes.
Got it.
So another question. In the case of LISA, the space telescope, how can you fix the distance? I mean, in the movement of the other bodies of the solar system should give a much larger effect than the gravitational waves. So you have to, how can you take that into account?
All right. For these space telescopes, we don't plan to keep the arm lengths constant to wavelength. We just let these satellites go. We have masses in all the satellites, which are similar to the Earth, and they move in the solar system. And they are influenced by all kinds of masses in the solar system. So they would move along, and this interferometer would breathe. So we will see the interferometer fringes all the time. But there's no influence that causes the distance between these masses to change on an hour time scale. So all the changes caused by astrophysical objects are monotonously, and they won't fluctuate on our time scale. And that's how we can deal with them.
Wasn't there a similar measurement by different method about a year earlier? They used polarized microwave background measurement. They claimed that they have measured gravitational wave then, but it was sort of refuted because of the possible interference by dust.
Right.
Now, do you think their measurement is totally erroneous, or do they have some validity?
I'm not in a position to really comment on their data. I mean, they took their claim back because they now think it was could have been, stopped by the dust, and I'm not in a position to comment on that.
Someone, yeah. Yes.
First, thank you very much for this very informative lecture. And I have a question is, would it be possible in future to detect other objects than black holes or merger of black holes?
We expect so. So we think we can detect not only mergers of black holes, but as well mergers of neutron stars. And neutron stars have much more information they could give us about material at this high density. It's very dense, they're formed from newtons, there's a lot of physics involved, and we could learn a lot by detecting gravitational waves from neutron stars. There's another thing which is pulsars. So if we have, for example, neutron stars, I mean this was a merger of two neutron stars. We could as well have a neutron star rotating by itself, and if there was a small asymmetry on this neutron star, something that happens in the crust of a neutron star, that would produce an asymmetry, and by that would cause a gravitational wave as well. And then, I mean, when Galileo took his telescope and for the first time looked into the sky, he saw a lot that he didn't expect. And I'm pretty sure that we will see a lot in this dark universe, which we're just not able to detect with light, that comes up once we are in this phase of really gravitational astronomy. It could go as far back as to the Big Bang. All information from the Big Bang we have is from some time, couple of 100,000 years after the Big Bang, because all light was reabsorbed in there. But gravitational waves would travel immediately from the Big Bang towards us.
Perhaps total new objects.
Yeah, that would be the most exciting detection.
Thank you. Also, it's very interesting. I want to be convinced also. And how is it possible that not LISA in the outer sphere is more sensitive than you can build that you can build a device under the Earth? How it is possible to measure something, at least the Earth and not outer space? And the second question is, how is it related to the device of the Michelson-Morley experiment? Some people say it's quite similar, but just more sensitive. Thank you.
So let me comment on the second question first. It's basically the same measurement principle as these Michelson-Morley experiments, and it's just more sensitive. So those people who say that are wrong. It's a factor of a million billion more sensitive. Now the other question is a good, very interesting one. Why wouldn't these space detectors not be more sensitive than the ground detectors? Why do we have to build these detectors underground? Now, if you imagine that these gravitational waves shorten and expand the arms, okay, that's the effect what they cause. So we send light to the far mirror and it comes back and measures the distance here. Now, if the distance is now changing one period, it comes shorter, longer, and back, then you would measure no distance change, because for half the time the arms would get shorter, and for the other half the arms would get longer. So you can't measure any distance change. That means if this gravitational wave moves these mirrors too fast, then the light in the laser would just be in the arms and average over each period. It would average over many, many periods, and that's the reason why we are not able to measure the gravitational waves at frequencies that changes these arms by, say, once per second or faster with laser.
Any other questions? Yeah.
Thank you very much. This was noise from the very close universe. When you say that that we will try, that you will try to detect a merger of neutron stars, and the mass of neutron stars is much less than the mass of black holes. I suppose that the influence on the waves that you should detect is on the amplitude or the wavelengths. But what is the problem now? Technology doesn't detect such very, very tiny wavelengths or amplitudes, or if they're still a theoretical problem?
This would be the best curve here. So this is the sensitivity of the detectors that we had, and this is the sensitivity of the detector that we could have now, the advanced LIGO detector. And we are currently a little, or more, almost a factor of 3 above that, because we haven't yet optimized our detector. Black holes are in this region here, a couple of tenths of hertz. Now neutron stars are smaller, they come closer to each other and collide at higher frequencies. They can circle more often around each other, faster, and collide at higher frequencies. But you see, our sensitivity towards higher frequencies, at least up to 300-400 hertz, gets better. So we should be able to detect now a neutron star in spiral out to something like 70 megaparsec. We were just not lucky enough that such an event happened during our observation period. So we hope that with the next observation period, we might see one, and we have still a room of 3 in sensitivity, which means 3 times 3 times 3, almost a factor of 30 more events in the same time that we could see. So the rate of these events that we can see will increase with increasing sensitivity, and we might then get lucky in the next observation run, which starts in September. For another half year, we might see one already. So no new technology, same detectors. We just have to wait. And if we then take another factor of 10, then we're pretty sure that latest then we will see something.
I just want to add something to this question about the polarization measurement. Actually, it was announced by the BICEP 2 collaboration, and the Planck collaboration immediately questioned it, and since then they published it together, the official rejection of the effect. So it is really true, they announced together that it is due to interstellar dust and not gravitational waves.
Okay.
Okay, I'd like to thank Benno Willke for a very exciting talk, and I'd before you applaud, I'd like you to please remain for a few minutes because Renata has to tell you about how to get to the place where the dinner is tonight, okay? So first let's thank Benno very much. You're not gonna say anything? You won't.